Okay, so last thing to talk about in this unit is power. We don't really have to deal too much with the math of power in this, but we do need to understand what power is, relationship between power, force, and velocity, that kind of stuff, but we don't have to do much problem solving, okay, any problem solving to do with power anymore, okay, because they changed the curriculum. So the biggest thing to know about power is that power tells us how quickly work can be done, not how much. Okay, that is the big thing about power. I mean, yes, obviously, if I had two machines, one being twice as powerful as the other, the twice as powerful machine would do more work in an hour. Okay, but if time's not a factor, a less powerful machine can do just as much work as a more powerful machine. Okay, and in some cases, we don't want a job to get done quickly. Okay, we want the job to get done reliably or consistently or something like that, because as we've all seen, sometimes more powerful machines have a higher likelihood of breaking down. Okay, if there's more power, there's generally more force, okay, and things like that, and so there's a higher likelihood of things breaking down. So there's always a trade-off, right? It's not always a perfect world where I just want more power. Okay, most of the time that's what we want, but okay, and it doesn't always work out necessarily the best when we choose that. Okay, so in lots of situations, the time it takes to do work is just as important as how much work gets done. Okay, so we would want a more powerful situation. So if we have these two like Honda Civics, they're like 1992, like the original Fast and Furious model kind of Honda Civics here. Okay, this would be the stock model, which would go from 0 to 60 in about 2 weeks. Okay, and then there would be like the modified one that has like 3 turbos and a bunch of other crap on it. Okay, so that it accelerates to 60 miles per hour much faster. Okay, it's more powerful. It can do that job, accelerate the car to 60 miles an hour more quickly. Okay, than the less powerful one. Can this one get to 60? Yes. And the wind behind it, downhill. Okay, it can get there, but it's not as powerful. Okay, it's not doing that job as quickly. All right, so that's the big thing here about power, is that more power just means the job is done faster, not that the job doesn't get done with a less powerful machine. Okay. Now, units for power, because obviously when we're looking at car engines, lawnmowers, snow blowers, whatever, okay, we always rate those in horsepower. Okay, horsepower is like an imperial unit, and in fact, horsepower is not actually a real unit; it's foot-pounds per second. Okay, which is also an imperial unit. In the metric system, the units for power are watts. Okay, and in fact, now on some like if you go to the car dealership, the new car dealership, sometimes the power is actually listed in both watts and horsepower on the sticker on the car. The watt number, even to me, is completely meaningless. And I walk up to a car and it's like 30,000 watts. I'm like, is that good? 60 watts is a light bulb. Is 30,000 good? Is that powerful? I don't know. Okay, it's not a number that means a lot to us because we're used to hearing different units. Okay, so we'll talk a little bit about the units here in a bit. But understand that because power is work divided by time, the units are joules per second. And that's a watt. Okay, a watt is a joule per second. Okay, so if you have a 1,000-watt microwave or an 1,100-watt microwave, which is a pretty common rating for a microwave, it's going to use 1,100 joules of energy every second, or deliver 1,100 joules of energy to your food every second, which is why it can heat stuff up so quick. Okay, that's a lot of energy to be absorbed by something. Okay. All right. So I have these two devices. I have the water wheel on the left. I have Grand Coulee Dam on the right. Okay, they are both essentially hydroelectric generators. Or we'll say the one on the left is. It's not really, but that's what we'll say. Okay, they can both generate electricity. If I run this one for 1,000 years and this one for a minute, they'll generate the same amount of power. Maybe, probably not. Probably like a second for this one. Okay, but yeah, obviously this powers the Pacific Northwest. That would be Washington, Idaho, and Oregon. Okay, this keeps a light bulb on, something like that. Okay, they do the same job. Okay, but obviously the more powerful one does that job a lot more quickly. Okay, and so that's what we just have to remember, is that the units for power are watts. Okay, a joule per second. Okay, so there's other formulas we can derive from that. If power is work divided by time, work is also force times distance. So we could say that power is force times distance over time. But what's distance over time? Speed. So we could also say it's force times speed. There's a whole bunch of different ways to calculate power, none of which you're going to have to use. Okay, it's just important that you know that we can do this calculation in a number of ways. Okay, a lot of things relate to power. Okay, something that is more forceful will generally be more powerful. Okay, or something that is faster is generally going to be more powerful. Okay, force and speed, okay, or work and time, okay, whichever, those all relate to how powerful a machine is. Okay. All right, so when we're talking about in the imperial system, okay, the units for power is a foot-pound per second, right? The reason we translated that into horsepower is because when the internal combustion engine came out and they were putting it in cars and tractors and such, people wanted to know what? How many horses will this tractor replace? That's what they wanted to know. Okay, that's where the unit's horsepower came from. Okay, when Farmer John was looking to pull his plow with a tractor instead of a team of horses, he went into the John Deere dealership and said, "What? How many horses will that big green monster replace?" Okay, so that's why they had to come up with horsepower. Okay, they needed to have some equivalent of what a horse could do. So they ran this experiment. They hung a mass over a shelf and had a horse pull it. Okay, if the horse could pull it at 1 meter per second, they added more mass. Okay, until the horse could just barely pull the mass at 1 meter per second. Okay, then they were able to figure out the force because they was pulling a weight. So we just had to go mass times gravity times 1 meter per second. Okay, and so that allowed them to figure out that a horsepower is about 550 foot-pounds per second, or 746 watts. Okay, that's what 1 horsepower is. So if you put a horse on a treadmill and had him run, he could power 700-watt light bulbs. Seems kind of wasteful, but that's what he could do. Okay, 1 horsepower is 746 watts, which means when you run the microwave, that's more powerful than a horse, because your microwave is 1100 watts. So if you hooked up a horse to the microwave, it would take longer to heat up your lunch than it would if you just plugged it into the wall. Okay, sad day for horses, right? But obviously, as the internal combustion engine got better, it replaced a lot of horses. There was probably an excess of glue for quite a while. That's always what they say they do to the old horses. They take them to the glue factory. Okay, yeah, it's sad, but true. Okay, so yeah, that was the whole idea behind this. I mean, horsepower is not a real thing. It's 550 foot-pounds per second. Right, that's what a horsepower is. Okay, we just translated it into something that was more meaningful. Okay, not that it's meaningful now, because very few of us have horses that we're replacing. Okay, but obviously at the time that's where it came from. All right, so if I have, actually, you know what, we don't have to do a calculation, so we're going to skip that. Okay, so like we say, power is force times speed, okay, and we can take that average speed, multiply it by the force, and calculate the power of something. Okay, in the case of this car, it's a bit artificial, but that car would only have 78 horsepower, which is ridiculous because that alcohol-fueled funny car is probably closer to 1,500 or 2,000 horsepower. Why is it so much more powerful than what the equation says it should be? Where is this equation set? In the perfect physical world where the car only has to accelerate itself and not work against any non-conserved forces and not spin its tires and. Okay, a lot of energy and power is wasted, okay, when we're doing stuff in the real world. So yeah, if it was a perfect physical world, that car would only need to be 78 horsepower, which is less than a smart car. Yeah, weird. Okay, so we're going to look at this little activity here. This I think I did put in your notes package, didn't I? Yeah, Okay, so just go to this. We're going to look at how much power Yoda could generate. Okay, it comes from this. The idea for this actually comes from this like kind of tongue-in-cheek article that was written about using, if Superman existed, could we like use him to power the world? I mean, theoretically, you could do that. You just have to know how powerful he was. So this was changed a little bit to Yoda. So okay, if we had like a bunch of the wind turbines like they have down in Pincher Creek, okay, we just put Yoda down there, and he would go, rotate your wheel, and off we would go, and we would have all kinds of power there, okay, to go. Okay, so we're going to look at, okay, Yoda's greatest display of raw power in the original trilogy. So first I'll show you that. Okay, that was when he lifted Luke's X-Wing out of the swamp on Dagobah and moved it over and then set it down on the shore. Okay, that was his greatest display of raw power in the original trilogy. We're not going to look at the prequels because they just get ridiculous. Okay, and he burned down the Jedi Temple in The Last Jedi, but we're not even going to talk about that because it's just a debacle. Okay. Ruined Johnson, just ruined everything. But anyway, okay, we're going to just look quickly at that video and then we'll talk some more. Okay, we have the energy it takes to lift an object. Okay, we know this formula already because it has to do with potential energy. Is the object's what? Okay, what three things do we multiply if we want to get the work done to lift an object? Mass, gravity, and height. Okay, so we need to know the mass of the X-Wing. Okay, we need to know the acceleration due to gravity on Dagobah, not Earth, because this is not on Earth. Okay, so, and okay, the height that it's lifted. So watching that video, are we able to get any of that information? Not really, okay, but we'll figure it out because, well, you'd be surprised how far the fandom nerdom goes. Okay. All right, so first we have to establish essentially the mass of the ship. We don't know that, okay? The X-Wing's mass has never been canonically defined. That means it's not in Star Wars canon, which is like, if you're not aware of what that means, canon means it's the stuff Disney says is true now, okay, versus the stuff that might be written in books and other things, okay? No one has ever said what the mass of an X-Wing is. So we're going to figure it out. We're going to approximate it. Okay. We know that its length for some reason is in canon. It's 12.5 meters long. Okay. An F-22 fighter, which is a real aircraft, is 19 meters long and weighs 19,700 kilograms. So we'll scale back and we'll say that the X-Wing is about, sorry, that should be kilograms, 12,000 kilograms. Okay. Or 5 metric tons, something like that. Okay. Sorry, not. That should be pounds. Sorry, that is pounds. This should be pounds too. Okay, so we're going to say that the mass of the X-Wing is, 5,600 kilograms. Okay. So now that we have that, okay, we know its approximate mass. We need to know how fast it was rising. Thankfully, the guy who made this, who wasn't me, believe it or not, okay, he's even more nerdy than me, took the time and effort to review the scene that we just watched, and time how long it took the landing strut to get out of the water. Then he went back to Star Wars Episode 4 and he used a scene where someone ducked and went underneath an X-Wing to approximate the height of the landing strut so that we could figure out just how quickly the X-Wing was being lifted out of the water, because people do this because they have way too much time on their hands. Okay, so so he went over the footage, okay, of the rate of ascent. Okay, the front landing strut rises out of the water in about 3.5 seconds, and he estimated the strut to be 1.4 meters long based on a scene in A New Hope where a crew member squeezes past it, which tells us the X-Wing is rising at what rate? Okay, we know it's going to move 1.4 meters, and that takes 3.5 seconds. What formula do I use here? Speed is... Oh my gosh, you guys don't remember how to calculate speed? D over T, right? Speed is distance over time. 1.4 meters over 3.5 seconds. Okay. Whoop, divided by. All right, so 0.4 meters per second is the speed at which the X-Wing is coming out of the water at. Okay, lastly, we need to know the strength of gravity on Dagobah. Okay, so here he figures he's stuck because while sci-fi fans are obsessive, it's not like there's going to be a catalog of minor geophysical characteristics for every planet in the Star Wars universe, except that he's totally wrong about that. There's a website called Wikipedia. Chewbacca is a Wookiee. Okay, if you don't know who Chewbacca is, crawl out from under the rock you have been living under and watch Star Wars. Not Episode 8. Don't watch that. Okay, don't watch that because it's crap. Okay, don't watch it. Okay, what? Do they? I don't know. I don't play them. No. Okay, so here's what we got. We found out, okay, from Wikipedia, who somehow found it out, that the acceleration due to gravity on Dagobah is 0.9 g. That means it's 0.9 times the acceleration due to gravity here. All right, so it's 8.829 meters per second squared. That's the acceleration due to gravity where Yoda lives. Okay, so we want to calculate now, okay, the power that Yoda has, the power he has to move things around. So I need to calculate how much work he did to move the X-Wing and divide that by how long it took him to do it, okay, because it's work divided by time. Everybody all right with that? Or it could be force times velocity. Either way it'll work, okay? But we're going to use the total work done divided by time. Okay, so we're going to take m times g times h, and then we're going to divide that by t. So we'll have the 5,600 kilograms we were given times 8.829 times 1.4 meters. Okay, and then we're going to divide that by the 3.5 seconds that it took for him to do that. All right, so that's 19,776. We'll round it to 77 watts. 19,776 watts. That's about 25 horsepower. Seems like not very much for Yoda. Okay, so I'm assuming then that would mean we would not be able to meet our power needs using Yoda by himself. We could have a whole bunch of Yodas, maybe it would work. Okay, but it's not going to work. Okay, so at current electricity prices, Yoda would be worth about $2 an hour. Not even minimum wage, not even close to minimum wage. Okay, poor guy would just stand there and rotate windmills and make $2 an hour. Okay, now looking at other examples of like power that's generated. Okay, if you're looking at like the telekinesis part, yeah, that's moving things with your mind. Obviously, that doesn't look impressive when we calculate the numbers. But if you start looking at scenes in Star Wars where they like shoot electricity out of their fingertips, okay, the Sith lightning, okay, that's like super powerful. In order to make electricity arc even over a short distance requires huge amounts of power. Okay, those would be something on the order of like 10 kilowatts. Okay, something like that. So a lot more energy. Okay, but of course our current energy demands are in the megawatts. So yeah, it would be quite a bit more. Okay, so if we look at Luke, okay, if there's a scene in Empire Strikes Back where he pulls his lightsaber out of the snow and kills the big Wampa ice creature, okay, or cuts its arm off, doesn't kill it, probably killed it, okay. He went through that frame by frame and found that Luke had a power of 400 watts as opposed to Yoda's 19,000, okay. So that's a fraction of Yoda's, okay, which kind of makes sense. He wasn't trained yet and things like that. So there's actually some like reasonable mathematical ratio backing to a lot of the stuff that you see there. I mean, it's all, we make it all up, but it's all kind of there, okay. It kind of makes sense. All right, I want you guys to answer those 3 questions there, and I think there's a couple more. No, just those 3. I want you to answer those 3 questions there, okay, and then we'll talk about those here in a minute. Okay, so I'll give you a couple minutes on those 3. Okay, so let's have a look at these 3 questions here. So first, the free body diagram of the X-Wing fighter while it's still in the water. Okay, so here's the X-Wing. Obviously, gravity would be one of the forces pulling down. Okay, there's only one force pulling up, and that's Yoda. Okay, so we have force of Yoda there. Okay, are there any other forces while it's still in the water? Real world forces. Force of the water. Okay, there's water resistance. Moving something through the water is harder than moving it through the air. Okay, so we would say friction. And usually if something is in the water sitting on the bottom, you ever notice how if you get your boot stuck in mud, it's hard to pull it out again? Okay, there's that kind of suction that happens there, so there could be the force of it being stuck to the bottom, okay, of the marsh, and this is obviously a marsh, so it's not a rocky bottom, right? It would be really muddy. Okay, so something like that. Okay, we could just say force of being stuck. Okay, something like that, right? So there's a lot of forces there, which means that the number we calculated isn't a really reasonable estimation of what Yoda did. He had to overcome more than just the force of gravity. We only took into account the force of gravity. Okay, there would be force of friction, force of being stuck. There might be one more upward force, and that might be buoyancy. Okay, as long as the X-wing wasn't completely filled with water, there would be some amount of buoyancy left in it due to the air inside. Okay, probably be a small amount, but it would have been there. All right, so yeah, you know what? He probably did more work than the 19 kilowatts we calculated. All right, now for part 3, this is the most important part. How much work did he do while moving it horizontally? We calculated how much work he did to lift it. When it moved horizontally, okay, its height didn't change, its speed didn't change. How much work did he do during that part? Speed didn't change, height didn't change. None. Okay, it takes no work to do something that doesn't change any energy. Okay, it moved at a constant velocity, so its kinetic energy didn't change. He moved it horizontally, so its height didn't change. That means he didn't change either potential or kinetic energy during the horizontal part of that movement. So he did no work during that part. Okay. All right. Now, last thing I want you guys to have a look at here. This is in your notes after Newton's third law. And it's what happens when everybody jumps. Okay, we talked about this because I talked about in terms of that Super Bowl commercial from last year where everybody ran and reversed the spin of the earth, which was stupid. Okay, so I want you guys to read through this thing here on what would happen if everybody jumps. Okay, and then there's some questions on the other part of it, okay, that I would like you to try. Okay, they're right here, 1 through 8. All right. So a couple of things here, guys, that we're going to assume for our purposes, okay, and that is that the world has 6 billion people on it, okay, we'll make that number, okay, our population number, so 6 billion people, okay, they're giving us that the average mass of a person on Earth is 65 kilograms, okay, so from there, you guys should be able to do the rest of those calculations, okay, so like I say, this is in the notes package, so give it a read, and then we'll talk about the article itself. Then I'll give you a little bit more time to work on the 8 questions, and then we'll talk about those before the bell goes. Okay. First. Okay, so obviously the article does this a bit tongue-in-cheek in that it's talking about all the practical problems with everybody jumping in the same place. Not that they're not like serious problems if you were trying to actually do this, okay? But there's a few problems they don't mention. You have 6 billion people all standing together in one place. There's no mention of providing food, water, or sanitation. Gross. That's what I mean, sanitation, bathroom. Yeah, okay. Kind of gross to think about how much of that there would be with 6 billion people all in one place the size of Rhode Island. So, okay, there's obviously those problems that could be, well, let's say catastrophically world-ending if you could actually get everybody in one place. Okay. Then they talk about getting everybody out of there. Well, they were magically transported there. Getting them out of there, we couldn't do the same, I guess. So then we completely overload the transportation system and kill everyone. So yeah, there's problems there for sure. Okay. But what we're most concerned with, okay, would be the mathematical part of this. Okay, the mathematical concerns. Okay, based around whether we could actually knock the Earth out of its orbit, which is not the main problem with having everybody in one place. The problem with everyone in one place is everyone's in one place. Okay, so we need to, obviously we've kind of talked about number 1, okay, but what are some problems with the synchronization of everybody's jump? How big is this crowd? Significant, okay? It only takes you to be about 150 meters away from something for you to notice a delay between light and sound. All right, like if you're like at a track meet, for example, you're on the other end of the track, you're less than 150 meters away, and when the gun goes off, there's a noticeable delay between when you see the smoke and when you hear the sound of the gun. Okay, now we're talking about synchronizing this for an entire crowd. Okay, that could be miles and miles wide and long. Okay, and they're all supposed to react to one thing. Okay, this crowd would be so large it would be over the horizon. Okay, so you couldn't even use like a visual thing unless you put a light way, way up on a pole. Okay, but then you'd have this problem. Not everybody pays attention. Okay, so everyone's got to be looking at the light, waiting for it to go off to jump. And then you got problem of reaction time and all of that kind of stuff. You'd never make it happen. You'd never get everybody to jump at the same time. Okay, so the rest of this, guys, is a bit of math stuff here. So calculate the total mass of the Earth's population. Okay, not hard. We know it's 65. We know the population is 6 billion. Calculate the total gravitational potential energy when they are at the maximum height of their jump. Again, not a difficult calculation. Determine the kinetic energy of the crowd when they strike the Earth after their fall. That actually doesn't require any calculation. Okay, hopefully you'll figure out why. Okay, law of conservation of energy says that energy can't be created or destroyed, but the kinetic energy of the Earth will be less than that of the crowd. Write a sentence or two to explain that. Okay, number 6, determine the maximum kinetic energy of the Earth as a result of the crowd hitting it. Okay, again, think conservation of energy. All the energy of the crowd is going to get transferred to the Earth. All right, then calculate the maximum speed of the Earth as a result of the crowd hitting it. Okay, so another calculation there using kinetic energy, and then you decide whether there'd be any noticeable effect of that, okay, on the Earth. All right. One other number you're going to need is on your formula sheet, and it's the mass of the Earth. It's 5.98 times 10 to the 24 kilograms. It's on the back under other useful constants. Okay, so you will need that number as well. All right, I will give you about 10 minutes or so to get those calculations done. Shouldn't take you any longer than that, and then we'll talk about the numbers we get. Okay, let's quickly have a look at these. All right, so calculate the total mass of the Earth's population, assuming everyone is 65 kilograms. Okay, so quick calculation there. Okay, 65 times that's 6 billion. Okay, so there's the mass of the entire population of the Earth. 3.9 times 10 to the 11 kilograms. Okay, that is still on the order of several hundred billion times less than the mass of the Earth, of which that is actually part of, okay, because since we're on the Earth, we're actually part of the Earth's mass. Okay, so now that we have that, now we want to calculate the total gravitational potential energy. So that's going to be mass, that number we just calculated, times 9.81 times the 1/2 meter they said everybody could jump. Now, obviously, again, we're trying to average everything here. Not everybody can jump 1/2 meter, right? But okay, like there's some people who have a credit card vertical, right? They can't jump over a credit card on the ground, but that happens. Okay, we're just going to say for argument's sake it's 1/2 meter. So we're going to take that number, we're going to multiply by 9.81 and then times 1/2 meter. So there's the amount of potential energy that the crowd has while suspended 1/2 meter above the Earth's surface, all at exactly the same time. Now, when they come back down, that number becomes kinetic energy. That's why question number 6 didn't require any calculation. Okay, or sorry, question number 5 didn't require any calculation. Okay, obviously in the real world it would be different because when you hit the Earth's surface, it's not rigid. Okay, you'd make footprints and there'd be sound and all of that other kind of stuff. Okay, yeah, we get it, but we're going to say it's perfectly rigid and all energy is conserved because that makes it simpler, right? So now the maximum kinetic energy of the Earth as a result of the crowd hitting it is still that same number. Okay, if we're still using law of conservation of energy, that's the amount of energy transferred to the Earth as a result of the crowd landing. So now we can calculate the speed that the Earth would pick up because of this. All right, so we're going to take that number and we're going to divide by 1/2 of the Earth's mass. And then we're going to square root that. All right, so 8 times 10 to the negative 7 meters per second. So what's that? 1 like 10 millionth of a meter per second. Okay. Probably not going to worry about that knocking the Earth out of orbit. Probably, definitely not going to worry about that. Okay. Everybody follow me there? Plus, like we say, the Earth is not a perfectly rigid ball. Okay, even if we could do this, all it would do would be to, compress the dirt there a little bit. Okay, and that would be about it. Okay, because the Earth is actually kind of malleable that way. Okay, plus there'd be all the seismic stuff that would happen. A lot of that would just become vibrations within the Earth, which would be damped by the mantle and all of that kind of stuff. Okay. So vibrations like that would just pass through the Earth and eventually dissipate. They wouldn't move the Earth out of orbit, okay, in any way, shape, or form. All right. So obviously, question number 8, the answer is no. There would be no noticeable effect, okay, on the Earth due to the jumping of the Earth's population ever. All right. So now you know, and now you know why that Nike commercial with everybody running is just stupid. Okay. All right. So guys, Law of Conservation of Energy Labs, due Friday. Okay, make sure you have them done. Okay, unit exam, day after tomorrow. Okay, make sure you're preparing, studying for that. I've only had a few people come in and ask questions, so I'm hoping that means everybody just knows everything and not that they haven't started studying yet. Because, oh my gosh, please say that's not the case. Okay, yeah.